In this video, we're going to give Hacker Sidekick a recently patched vulnerability and watch it build a working exploit from scratch. It pulls the source code, figures out what's wrong, sets up a test environment, writes the exploit, validates it, and produces a full report. No follow-up prompts, no hand-holding, just the CVE and a description of what we need. The vulnerability is CVE-2026-23918, a memory corruption bug in Apache's HTTP2 module that was patched 4 days before we recorded this. It crashes the server reliably and has a potential path to remote code execution. The whole process took about 40 minutes in real time. We've sped it up to make it easier to watch, but nothing has been cut. Every step happened exactly as shown. First thing we do is create a project folder. Hacker Sidekick works like an IDE, so giving it a workspace means it can read and write files, manage the project structure, and keep everything organized as the exploit develops. Now we describe what we want. It starts by researching the CVE. You can see it searching the web, pulling in advisory data, patch details, and any existing analysis. It's building its own understanding of the vulnerability before it writes a single line of code. From that research, it produces a full exploit development plan, target surface, hypothesis about the trigger mechanism, constraints, safety boundaries, and a staged approach broken into 7 milestones: research, environment setup, denial of service, proof of concept, detection variant, RCE exploration, validation, and documentation. It's important to note that at this step, you can always stop Hacker Sidekick and change the plan so that it executes to your expectations. It then asks for approval before proceeding. This is Hacker Sidekick's checkpoint system. It won't start heavy implementation or run anything against live targets without explicit sign-off. We approve the plan and we let it run. Stage 1 is source research. It downloads the vulnerable and patched versions of Apache, extracts them, and diffs the mod HTTP2 module. 284 lines changed. It reads through the diff and identifies the root cause. 2 cleanup callbacks in h2 mplx.c can both push the same stream pointer onto a purge array, leading to a double free when the array is iterated. Stage 2 is the lab environment. It builds 2 Docker containers, one running vulnerable Apache 2466 with mod HTTP2 and SSL enabled, and one running the patched 2467 for comparison testing. The config enables HTTP2 over TLS on port 8443 with the event npm. This matches a realistic production deployment. Stage 3 is the actual exploit. It writes a Python proof of concept that handles the full attack chain: TLS connection with ALPN negotiation for H2, raw HTTP2 frame construction, the headers, then RST stream trigger sequence to raise the stream lifecycle callbacks and induce the double free. It builds in 2 modes: a denial of service mode that fires rapid RST stream frames to crash worker processes, and a detection mode that produces a slower, fingerprintable pattern for testing your detection rules. With the denial of service working, I decided that would move forward with RCE exploration and skip the drip version. It analyzes the heap layout, examines the freed H2 stream object, looks at APR pool T internals, and assesses whether an attacker could control the freed memory to redirect execution. It writes a heap grooming script that demonstrates the concept. Spray HTTP2 header fields to shape the heap, trigger the double free, and then attempt to reclaim the freed slot with attacker-controlled data. It's honest about the practical blockers, build variance, ASLR timing sensitivity, the denial of service is reliable and production ready, the remote code execution path is a research foundation, not a turnkey exploit. That distinction matters, and it documents it clearly. The final deliverable is a complete report, root cause analysis, the exact patch that fixed it, reproduction steps, RCE feasibility assessment with an honest verdict, and detection guidance including WAF signatures, network indicators, and log patterns to watch for. 8 milestones, all completed. The project folder has everything: the development plan, a running activity log, the proof of concept exploit, a heap grooming research script, a validation harness, Docker configs for both vulnerable and patch targets, and the final report. So there you go, a proof of concept exploit for a CVE that was patched just days ago. Researched, planned, built, tested, validated, and documented. 40 minutes, 1 prompt. If you had asked ChatGPT or Claude or Copilot to do this, you know what would have happened. You'd get a refusal and a lecture about responsible use. Every security professional has had that conversation. Hacker Sidekick was built for this work. It doesn't have that problem. If you want to try Hacker Sidekick for yourself, there's a link in the description.